Hi guys, welcome to the tutorial chapter 8.2. You have electromagnetic induction. Okay, I hope that you already try this tutorial question. Okay, so that I can help you to solve your problem. Okay, and you can complete all the answer for this tutorial 8.2. Okay. Before I show you the solution, before I show you the working and the step for this tutorial, okay, let's do some of revision. Okay, from this topic, you have some of the point. Okay, you need to remember. Okay, and also you need to consider when you want to do your revision for your final exam. Okay, here you have magnetic flux. Okay, remember how to calculate the magnetic flux. You have this formula. Okay, V equal to NBA cos angle. Okay, next you have Faraday's law and Lenz's law. When talking about the Faraday's law, you have a formula. Okay, the rate change of the magnetic flux. The rate change of the magnetic flux is equal to the induced EMF. Okay, next pipe. Okay, how to induce EMF when you have a moving straight conductor. So you have a formula to calculate the magnitude of your induced EMF of a moving straight conductor. And then how to show the direction. You need to apply Fleming's right hand rule. Okay, other than that, okay, you have the induced EMF in the rotating coil and the induced EMF in a coil. Okay, so let's look the tutorial question with the answer. Okay, again, for this tutorial, I don't want to discuss all the question. Okay, I choose some of question that I think that you have a problem, you have a question. Okay, so question one, you can refer to the notes. It's talking about the definition. Okay, the definition of term under this topic. So here I have a question 2, question 3, which is under the magnetic flux. Question 4, question 5, and question 16 also, which is the question, the problem is under the magnetic flux. Okay, formula to calculate the magnetic flux, you have P equal to NBA cos angle. Okay, for this part, it's very important for you to understand, okay, how to measure the angle. Okay, to substitute into your equation, substitute into your formula. Okay, that's the question number 2 here. You have a figure 1 show the side view of a circular core with 100 turns and the radius, okay, of circular core of 10 cm. Okay. Next, if the plane of the coil makes an angle of 50 degrees to the direction of the magnetic field B of the magnitude 3 Tesla, calculate the total magnetic flux through the coil. You want to calculate the magnetic flux through the coil. Okay, so you need to solve your question by using this formula. P equal to NBA cos theta. Okay, cos angle. So how to measure your angle? So refer to definition previously in your note. Okay, the angle you need to measure is, okay, the angle between the normal, okay, to the area with the magnetic field B direction. So where is the angle? Okay, normal, this is the normal of your plane to the B direction. Okay, so where is your B direction? This is your B direction. Okay, so you need to measure this angle the normal of your plane to the B direction. Okay, but in your question you are given the 50-degree plane to the B here. So you need to minus. Okay, how to calculate the angle here? 90 minus 50, then you got 40. So 40 substitute into your formula here. Is it okay or not? Okay, remember that if you want to use this formula, okay, the angle you need to use is the angle between the normal to the area or normal to the plane with the magnetic field B direction, not from the plane or from the area of your coil to the magnetic field B. Okay, don't confuse. Okay, is it okay? Then solve. You can got the final answer, the value of the total magnetic flux through the coil. Okay, next question. Question 3. Now you want to calculate the maximum and minimum. Okay, for the magnetic flux. So maximum value for your magnetic flux means you have the direction of your magnetic field B here parallel to the normal of the plane. Okay, the normal of the area here. This is the area, okay, of circular coil. So always perpendicular to the normal of the area, the normal to the area. Okay, so maximum means you have your angle is equal to 0. Okay, the normal of the area to the B is equal to the 0. Okay, when you got 0, cos 0 you get 1. So the magnetic flux is the maximum value. How about minimum? Okay, minimum means your B to the normal of your plane is 90 degree. So cos 90 degree, you got 0. 0, so magnetic flux is equal to 0. So minimum values of the magnetic flux linkage is equal to 0. Okay. Okay. Question 4, question 5, question 16 is the same like before. Okay, you want to calculate the magnetic flux. Again, here you need to consider the angle. The angle must be correct when you substitute into your formula of your magnetic flux and be a cos angle. Okay, for question 4 here, if you refer to your question, the magnetic field make an angle 30 degree to the normal plane of the coil. So if you refer this figure, okay, magnetic field B, okay, you have a magnetic field B direction to the right, okay, and then angle 30 degree to the normal, okay, 30 degree to the normal, so this is the normal, okay, so the angle is equal to 30, so directly you can substitute the 30 degree into your equation, into your formula. Okay. Question 15. Let's do the question. Okay, you have the plane of the coil max angle 30 degree to the direction of the magnetic B. Okay, plane of the cone max angle 30 degree to the magnetic field B. Not, okay, so you have plane to the B direction 30 degree. But remember, when you want to substitute the angle into your formula, the angle you need to measure is between the normal to the area, between the normal to the plane with the B, with the magnetic field B direction. So here for number 5, you need to minus 90 minus 40, sorry, 90 minus 30, then the angle substitute into your formula here. Okay. Next question number 16. Okay. This is under the magnetic flux, but now you need to calculate the change. Okay. Change in the magnetic flux means you have initial, you have a final for your magnetic flux. Okay. Let's put the solution. Okay. For question 16. Okay. Area equal to 72 times 10 power negative 4. Okay, and then you have a B, value the magnetic field B 1.5 Tesla. Okay, so you have a first condition. Okay, the inertial, so calculate the inertial magnetic flux through the coil. Okay, if you refer to this figure, the initially, okay, this is your plane. Okay, and then you have the normal of your plane here, always perpendicular to your plane. Okay, then you have a magnetic field B. If you refer back to your question, you have north and the south pole. Remember the direction of your magnetic field B, always from the north to the south pole. Okay, so B to the N, you have angle 90 degree. Okay, so you need to substitute the angle into your formula is 90 degree. The initial magnetic flux through the coil. Okay, angle initially and to the B is 90 degree. So initial magnetic flux you got 0. Okay, next, the final, you can rotate to 90 degree. Okay, you have a change of the magnetic flux. Rotate to the 90 degree. So what happened now? Okay, finally, okay, so your normal, okay, of the plane is to the right. Okay, which is parallel to the B. Okay, parallel to the B. So now, you need to measure the angle, the normal of your plane to the B, okay, is equal to 0. You have your N to the B parallel to each other. So, you have your angle, substitute, you need to substitute the value of your angle is equal to 0. Cos 0 is equal to 1. Okay. Then calculate the value of the final magnetic flux through the coil. You got this value. Okay. Next, you need to calculate the change in the magnetic flux through the coil. Okay, final minus the initial. Okay, so the answer is 10.8 times 10 power negative 3. We back. Is it okay? Okay. Next we go to the induced EMF. Okay. Before that, let's look the formula. Okay. To calculate the induced EMF, the rate change of the magnetic flux. Okay. dV over dt here. Okay. Is related to the Faraday's law. Okay. Question 6, question 7. Okay. You have a problem question which is under the induced EMF. Okay. If you refer to question 6 and question 7 here, you have a change in the magnetic field B. 2 millitensla to 3.5 millitensla in 0.2 seconds. Question 7 also, you have a change of the magnetic field B. Initially, you have 3 tensla and then reduced to 2.30, okay, tensla in 15 milliseconds. Okay, you have a change in the magnetic field B. Okay, and then divide by the change in the time. Okay, so how to solve for this question? Okay, let's do solution for number 7. Okay. Okay, question 7, solution. Okay, before that, let's read the question here. You have a circular coil of 100 turns. Number of turn is 100. The radius, okay, of your circular coil is 10 cm. Okay, placed in the magnetic field B of the magnitude 3 Tesla. The normal to the coil is parallel to the direction of the magnetic field B. Now, the normal, the N direction is parallel to the magnetic field B. So, means the angle between the normal of your plane, okay, the angle between the normal to the area with the magnetic field B direction is equal to 0. Okay, then if the magnetic is reduced to 2.30 Tesla in 50 milliseconds, so first determine the change in the magnetic flux in the coil, means you need to find the final, okay, magnetic flux, and then also the initial, final and initial of the magnetic flux in the coil. After you have a change in the magnetic flux, you need to substitute into your formula of the E. Okay, the induced MF is equal to the rate change of the magnetic flux. Okay, let's do the answer here. For question 7, solution. Okay, number of turns, you have 100. Okay, calculate area, the area of your circular coil. Okay, pi r square. Okay, and then you have a change of the magnetic field B, means you have an initial, you have a final of your B. Okay, calculate the initial magnetic flux through the coil. Okay, so here, how to calculate the magnetic flux? Again, you need to apply the formula. By applying the formula of the magnetic flux, NBA cos angle. Now angle is equal to 0 because of the normal of your plane is parallel to the B. So the angle between the N to B, okay, between N and B is equal to 0. Okay, final. The final magnetic flux through the coil, so B is equal to the B final, substitute the B final 2.30, B initial here 3, okay, and then how to calculate the change in the magnetic flux, final, okay, minus the initial magnetic flux through the coil, then you got this value 2.20 Weber, Okay, negative sign here, you got the negative sign. Okay, here indicate the flux was decreasing. If you refer to your question here, you have a decreasing value of your magnetic field B from 3 Tesla to 2.30 Tesla. Next, question B. You want to calculate the induced EMF. Okay, how to calculate the induced EMF? You need to apply the Faraday's law. Okay, by applying Faraday's law, the induced EMF is, okay, so the rate change of the magnetic flux. Okay, so here this is the change in the magnetic flux. Get from the first value. Okay, you got 2.20, divide by the change of your time. Okay, which is you have 15 millisecond. Okay, negative negative. Okay, here negative negative, then you got positive. Okay, so positive it shows here, okay, the decreasing of the magnetic flux. Okay, you have a flux here decrease. Okay, so decreasing magnetic flux has result in positive induce. Okay, so result here you have a positive for the induced EMF. Okay, is it okay? Okay, next question. Okay, question 10 is similar like before this. Okay, again here question 10. Okay, A, you need to calculate the magnetic flux when you have B perpendicular to the face of the loop. Okay, so perpendicular B perpendicular to the loop, perpendicular to the plane of the loop means you have B and N is parallel to each other. When you have direction of the normal of your plane and the B is parallel, okay, each other means your angle between the N and B is equal to 0. So you need to substitute into your formula. NBA cos angle is equal to 0. Okay. B, magnetic flux in the loop when you have B is 40 degree to the area A of the loop. Okay. B to the area of the loop or to the plane, okay, which is 40 degree. But again, remember you need to substitute the angle normal to the B. So here you need to minus 90 minus 40, then you got 50. Substitute into your formula. Okay. Next question C, you want to calculate the induced EMF. You have a change in the magnetic flux. Okay, from position 10B to the position 10A in how many minutes? How many seconds? 0.15 seconds. Okay, so initial here and then you have a final. So final 10A. Okay, 10A you have 0.576 minus the initial. Okay, the initial magnetic flux through the coil you got 0.370. Okay, and then divide by 0.15, you got the induced EMF in the loop is 1.37 volt. Okay, here you got positive. Okay, you want to calculate the magnitude. Okay, so from this equation you can ignore the negative sign. Okay, is it okay? Next question. Okay, for question 8 here, you have a question problem which is under the induced EMF in a coil. Okay, here you have a change in the diameter. Okay, now you have a narrow coil of 10 turns, okay, the diameter of your coil change from 4 cm, okay, and then change to or increase to 5.3 cm. Okay, so when you have a change in the diameter of your coil, so means you have a change in the area of your coil. Okay, so if you refer to this solution, okay, let's see the solution here. Okay, you have a change in the area dA over dt. Okay, so change in the area, you have a change of the area final, okay, minus the initial. You need to calculate one by one the value of the area, okay, final, and then the area for the initial area of your coil. Okay, so minus then final minus the A initial. Okay, A final minus the A initial divided by the time. So you have a change in the area of the coil. A here. Change in the area of the coil. Okay. Okay. So here, this is your change in the coil A2 minus A1 or A final minus A initial. Okay. And then you have a time. Okay. 0.25 divided by the time you got the rate change of the area. The rate change of the area which is equal to 3.78 times 10 power negative 3. Okay, meter square per second. Okay, next you want to calculate, okay, the induced EMF, the induced current first. Okay, you want to calculate the induced current, but before that you need to calculate first you need to calculate the induced EMF, okay, by applying Faraday's law. Okay, the rate change of the magnetic flux E equal to dP over dt. Okay, here you have a change in the area, so dA over dt. The rest is constant for the B and N. Okay, angle is equal to 0. Why your angle is equal to 0? Refer back to your question. You have your means here you have the plane, the N, okay, perpendicular to the field. So N, the normal, okay, of your plane direction is parallel to the magnetic field B. Okay, the angle is equal to 0. So you got 0 here. Okay, substitute the value of change in the area, okay, the number of turns and the value of the magnetic field B, then you can calculate the induced EMF. Okay, 0.0454. Okay, after that, by applying the Ohm's law here, okay, E equal to IR, okay, or you have V equal to IR, but now the value of your voltage is equal to the induced EMF, so you have E equal to IR, and then calculate for the induced current E divided by R. Okay, here R you have is 2.4 ohm. Okay, so solve this one. You got the induced current 0.19 ampere. Is it okay? Okay. Next. Okay. Next question, you have induced MF in the rotating coil. Okay. So, before that, let's do the equation here. To calculate the induced MF, when you have the question or problem, okay, in the rotating coil, means you have a coil rotate, okay, in the magnetic field B, cutting the magnetic field line, so we'll produce the induced EMF. Okay, but now your equation for the induced EMF is equal to E equal to NBA omega sine omega t. Rotating coil, rotational motion, so you have a term of the omega. Okay, then if you want to calculate the induced EMF in the maximum, okay, point, the equation is equal to NBA omega only. Okay, so I have answer here for question number 13. Okay, so let's do the question here. You have an AC generator consists of the rectangular coil. Okay, six-seater rotating about its central axis in a uniform magnetic field where B is equal to 0.5 Tesla. The dimension of the coil are 8 cm by 6 cm. So the area of the rectangular coil is 0.08 times with 0.06 meter. Okay. So you have area value, and then the B 0.5, 0.45 Tesla, and is 60 ton. Okay, next omega. Omega unit is radian per second. Okay, remember the unit for the angular frequency here is radian per second. But your question, your problem is given the value of the omega in unit revolution per minute. Revolution per minute. So first you need to convert to the radian per second. Remember how to convert? Okay, I show you here the conversion unit. Okay, you have a conversion factor here, 2 radian. 1 revolution is equal to 5 radian. 1 minute is equal to 60 seconds. So convert first. Okay, 4500 revolution per minute to the radian per second. Okay, then you got the value of your omega. Substitute all the value into your formula here. E equal to the, okay, NBA omega. Okay, to calculate the value here, okay, which is the value is equal to 61. Okay, the whole thing here, you can try to calculate this value, and then sine. Okay, refer back to your equation here. You have a sine omega t. So sine omega t, omega. Okay, 1505. Or you can solve 150 time with the radian. Okay, also you can write in terms of the value, or you can write in terms of the pi here. Okay, so E is equal to 61 sine 150 pi t. The expression of the induced EMF has a function of the time. Okay. Question B, you want to calculate the induced EMF at 1.5 second. Okay. From your question A, okay, E equal to 61 sine 150 pi t. Okay, then substitute the value of the time t with 1.5 second, and then solve your equation, your formula. Okay, make sure you change your, before you press your calculator. Okay, change your mode calculator to the radian because your omega in the unit radian per second. So mass in the radian. Okay, mode of your calculator. Okay, and then solve one by one. Solve for the sign here first. Okay, and then time it is 61. Then you got the final answer which is E is equal to 0. Is it okay? So if you refer to question 14, this is also under the inducement in the rotating coil. Okay. Here, now before that you have your induced EMF here for part A. Okay. Change in the magnetic field. You have a change in the magnetic field dB over dt here. Okay. So here dB over dt. Okay, again, to calculate the induced EMF, okay, you need to apply, okay, by applying Faraday's law, okay, E equal to the rate change of the magnetic flux, okay. Solve for this question, okay. Question 14b, this is the under the induced EMF in the rotating coil, okay. You want to calculate the maximum induced EMF, okay. Sorry, you need to calculate the number of turn here, but you are given the value of the EMF at the maximum. So here you need to use this formula. Okay, you have your frequency value. So from the omega, okay, is equal to 2 pi f. Okay, I think you are very familiar with this formula to calculate the omega is equal to pi f. Then you can calculate the omega, then substitute the value of your omega to your equation here, E maximum, then solve for the n number of turn. Okay, is it okay? Okay. Number 17 also under the induced EMF in rotating coil, but now you have a graph. Okay, you are given the graph. You need to find some of the values and information input from this graph. Okay, let's do the question here. You have the coil generator has 150 tons. Okay, area, you are given the area of your coil 350 cm square, convert to the meter square. Okay, it is rotating, so rotating. So you have an induced EMF under the rotating coil problem. Okay, in the magnetic field of the magnitude of 0.20 Tesla. Okay, your figure show the induced EMF in the coil is varying with the rotating time. Okay, question A, you need to calculate, okay, period of the coil rotation T. Okay, you can refer to your graph here. Period is equal to 1 complete cycle. Okay, next question B, angular frequency, which is omega. Omega is equal to pi t. Okay, substitute the value of the t from A into your equation here to calculate the omega. Next question C, you want to calculate the EMF generated, okay, or the induced EMF when the coil is rotating at instant when t is equal to 0.10 second. Okay, so in induced EMF in the rotating coil, you have a formula E equal to NBA omega sine omega t. Okay. the equation of the induced EMF as a function of the time. So substitute the value of your time here, okay, with 0.10 second. Okay, you have number of turn, you have a B value here, and then you have your area convert to meter square. Okay, and then you have your omega value from the part B here, 52.36 sine. Here you have also omega 52.36. Okay, again for this question, when you use this formula, this equation, you need to choose radian mode when using the calculator. Okay, make sure you change your mode calculator to the radian and then solve one by one. Okay, so for the sine here, the sine part here, and then time with the rest value here. Okay, now you got the negative sign for the induced EMF, negative 47.61 volt. Why you got negative? If you refer to this question, when you have a T around 0.10, okay, the value for your E is negative. Or you can refer back to your notes. You got this type of your graph. Okay, the sinusoidal alternating EMF. Okay, so you have the value of your E. Okay, negative, and then you have a positive. Why is due to the direction of the rotating coil in the magnetic field B here. So it's due to the direction. Okay, is it okay? Is it clear? Okay. So next, let's do the last part here. You have an induced EMF of a moving straight conductor. Okay, you have a question number 11, number 12, and number 15, which is under this part, induced EMF of a moving straight conductor. You can induce an EMF, okay, when you cutting the magnetic field B. Okay, or you refer here, or you refer to this figure. They say this is okay, this is your conducting, okay, your straight conductor. You have a magnetic field B here, direction into the page. Okay, so when you move your straight conductor to the right, or you want to move your conductor also can to the left, okay, means cutting the magnetic field B. So you will induce the EMF. Okay. So when you have the problem, the question which is under the induced EMF of a moving straight conductor, now your formula, okay, is equal to the E equal to the VLB. Okay. Previously, you have induced EMF in a coil. You have an induced EMF in the rotating coil. You have a different formula. Okay, and also you have induced EMF, which is related to the Faraday's law, direction of the magnetic flux. If you refer back to your notes, okay, you have a derivation. Okay, this equation is come from the definition, okay, of equation of the Faraday's law, which is the rate change of the magnetic flux. Okay, so V here is refer to the velocity of your conducting, okay, of your conductor here. L is refer to the length of your conductor, or here also. Okay, you can refer also this figure. You have the length of your conductor. B is the magnetic field B. Okay, value here. Okay, you can see the direction here into the page. Okay, here you also, when you apply the magnetic field B, direction into the page. Okay, so when you have a question problem under the induced EMF of a moving straight conductor, how to calculate the induced EMF? What is the value of the voltage? What is the value of the EMF? Okay, you need to apply this formula. Okay, E is equal to VLV, and then this is formula to calculate the induced current. When you have an induced EMF, you have also induced current. So how to calculate your induced current? Okay, E divided by the R is referred to induced EMF. Or here you have an induced EMF VLB divided by the resistance of your conductor. And then you got the induced current. Okay, so this is the equation to calculate the value, the magnitude. This is the way how to show the direction. Okay, how to determine the direction of your induced current. Okay, remember, you have Fleming right hand rule. You need to apply Fleming right hand rule. Okay, before we learn detail about before I show you the answer about the direction by using the Fleming right hand rule, we go to the part of the calculation. Okay, which is to calculate the induced EMF, to calculate the induced current. Okay, let's do question 11 here. Okay, if you refer to this figure, it's clearly there is you can induce the EMF. Okay, moving, move. Okay, straight conductor here. Okay, you have your direction of your conductor to the right. Okay, so you can see the velocity of your direction, the direction of your velocity here for your conductor, on your conductor. Here also, this is the question problem which is under the induced EMF of a moving straight conductor. You have a conductor here, okay. It shows the direction of your conductor is going up. Okay. Question, you want to calculate the induced EMF. Okay, EMF produced by the rod. So formula E equal to VLB. Induced current, current induced in the circuit. Okay, E divided by R. Okay, power here, how to calculate power? You have IV. Remember the formula to calculate the power. You have IV, but V here is referred to the induced EMF. Okay, so IE to calculate the power. Okay, so it's good same with for question 12. To question 12, you want to calculate the magnetic field B here. Okay, but your question problem given is given the value of your induced EMF. Okay, you have your velocity of your straight wire, straight conductor, and then you have a length of your conductor. So by applying the formula here, E equal to VLB, okay, then calculate the magnetic field B. Okay, question B, okay. Now magnetic flux 0.15, the length of the wire is 40 mm. Okay, then you have a velocity if the wire moves at velocity of 1.2 millimeter per second. Okay, so you need to calculate the maximum induced EMF. Okay, direction I will show you later. Okay, let's do the next question, next problem, which is concept you need to apply. Okay, is the same with this concept. Okay, number 15. Okay, you have your straight conductor moving to the right here. Okay, and then you have your magnetic field B R page. Okay, so what happened? You will induce EMF, you will induce current. Okay, here you have a length of your rod 24 cm. Okay, resistance of your conductor 2.3 ohm. Okay, the speed, the velocity of your conductor 1.8 meter per second. Okay, magnetic field B apply is equal to 0.35 Tesla, and then you have your U-shaped conductor. The resistance of the U-shaped conductor, which is 226 ohm. Okay, the motion of the rod is perpendicular to the magnetic field B. Okay, the rod is perpendicular to the magnetic field B. In this MF again, here you need to apply the formula E equal to BLV. Okay, BLV. B, the magnetic field B value. L is the length of your conductor. V is the velocity of your straight conductor. Okay, and then solve. We got the answer for the induced MF 0.15 volt. Next, induced current. Okay, the current flowing in the U-shaped conductor. Okay, so induced current here, I equal to E divided by R. E is the value of your induced MF 0.15. The R here, okay, you need to refer back to your question now. You need to consider the resistance of the conductor, and also on the U shape, it's like you have a series connection. Your conductor, okay, conductor and your U shape here of your conductor. Okay, so what you need to do is you need to plus, you need to add the value 2.3 with the 226 to get the total of your resistance, okay, in your conductor. Okay, and then solve for the induced current here. Next, C, you want to calculate the force. Okay, needed to keep the rod's velocity constant at the instant. Okay, so to calculate the force, you don't have any formula for the force from this chapter 8.2. But remember, you have an equation for the force from chapter 8.1. Okay, remember when you place the magnetic field, when you place the conductor, okay, this is your conductor. This is your conductor. Placed in the magnetic field B will produce the force. You have a force. Your conductor experience the force, okay, due to the magnetic field B. So how to calculate the force? We have a formula ILB sine angle here. Okay, you have your conductor is perpendicular to the B direction. Okay, out of page, and then you have your conductor to the right perpendicular to each other. So sine 90, you got 1. Okay, and then solve for the force here, I L B. Okay, then you got the force. So is it okay? Okay, to calculate the magnitude. Now how to show the direction? Okay, let's look how to show the direction. The induced current. Okay, the induced current flowing in the conductor. Okay, so you need to apply by applying Fleming's right hand rule. Okay, okay. So here you have by using, you can try by using your right hand. Okay, you have your thumb. Remember, thumb it shows the direction of the motion of your conductor. Now you need to choose, okay, your thumb to the right, motion of your conductor. Okay, first finger that is the magnetic field B direction, your magnetic field B is out of phase. Okay, and then your second finger is the direction of your induced current inside your conductor. So I label here, I already labeled the conductor A and B here. So if you apply the Fleming right hand rule, you found that the direction of your current is from B to the A. The direction of your induced current inside your conductor is going up. Okay? Is going up. Okay, remember I have another figure or question which is under this part, induced MF of a moving straight conductor. For question 12. Okay, for question 12, you have your conductor moving, going up, okay, moving up, okay, and then you have your magnetic field B into the page, okay. So by using the Fleming right hand rule, you have your current, the induced current is to the left. Okay, let's show how to show the direction of your induced current by using the Fleming right hand rule. Okay, this is question 12 to show the direction of your induced current by using the Fleming right hand rule. Okay, thumb it shows the motion of your conductor, refer to the velocity of your conductor going up. Okay, first finger shows into the page because your magnetic field B into the page, and then second finger direction of the induced current. Okay, that's all for this tutorial 8.2. Thanks for watching this video.